morning. I am Renu Sharma, Assistant Professor EC Department. Today I am going to start with the next lecture for Unit 3rd, and the topic of today's lecture is MCM, that is Multicarrier Modulation Techniques, then Zero Intersymbol Interference and Communication Techniques. So, in this lecture we will discuss MCM, that is Multicarrier Modulation Techniques. When multiple users are using the same channel, then each user requires a different carrier signal that is delayed by some time interval, so that the carrier signal for each user, let's say 4 users are there, like this is the first user, second user and third user. So I am taking an example of 3 users, and these 3 users wants to access a common channel. So a modulation has to be performed at the transmitter side. For the purpose of modulation, we require a carrier signal. Let's say this is carrier 1, this is carrier 2 and this is carrier 3. So 3 carrier signals are there, and then the signal is added at the transmitter side, and then this will be the composite or the added version of the signal for the 3 different users. Now the carrier signals which I have taken here, these carrier signals need not to be same, because when the same carrier signals are there, then there will be an intersymbol interference will take place. So for that purpose, we have to take 3 different carrier signals which are delayed by some time duration, like this is t minus t1, this is t minus t2 and this is simply the t signal. So these are the delayed version of the carrier signal. Now these 3 carrier signals have to be used as same in the same manner at the receiver side, so that these signals, these S1, S2, S3 will be demodulated at the receiver side. So that is the main purpose of this multi-carrier modulation technique. Now if this multi-carrier modulation technique will not work properly, then zero intersymbol interference will occur. Intersymbol interference will occur, and we want to remove that particular ISI, that the interference. So for that we have to see a technique that how that can be made to 0. So this is the introduction of MCM technique. Now digital transmission through band limited channels cause intersymbolic interference. In such a case, the channel equalizer is employed at the receiver to compensate for the channel distortion. So what happened? Let's say a single user, I am taking an example of a single user, the pulse spreading will take place at the transmitter side on the channel. Whenever any user is transmitting the data in the pulse form, it will going to be spread due to the effect of noise, and that is known as the spreading of the pulses. And if there will be a noise which will going to affect the quality of the signal, then there will be a intersymbol interference will take place, that will cause the mixing of the signals. And like this is the pulse and this is for the second user, these 2 users data will be transmitted, and due to spreading of the pulse like this one, this intersymbol interference will take place, and this will causes the distortion of the information for both the users. So that is known as intersymbol interference. So in that case, we can use channel equalizer, which will going to equalize the effect of remove the effect of the noise which will causes the spreading of the pulse. So if the channel is a bandpass channel with a specified bandwidth, the information bearing signal may be generated at the baseband, then it is translated in the frequency to the passband of the channel. Thus, the information bearing signal is transmitted on a signal carrier. So, an alternative approach for this particular design of a bandwidth efficient communication is that in the presence of channel distortion or equivalently ISI, it is to divide the available channel bandwidth into number of equal bandwidth subchannels, where the bandwidth of each channel is sufficiently narrow so that the frequency response characteristics of subchannels are nearly equal. So, this is the approach behind alternative approach behind intersymbol interference, that how we can remove or how we can reduce the effect of that ISI. So such a division, if we are going to divide the particular bandwidth, overall bandwidth into a smaller sub channels, which is shown over here, like this is a graph which is going to divide the particular frequency band into equally divided bandwidth, then this is the equally divided channel. So we can create n is equals to w divided by delta f. Now delta f is nothing, it is the change of frequency or the frequency slots which are divided for this particular band. So where different information symbols can be transmitted simultaneously into n sub channels. So consequently the data symbol is transmitted by frequency division multiplexing. So we are using nothing, we are using FDM, that is frequency division multiplexing, and this is known as multi-carrier modulation. So in case of frequency division multiplexing, different frequencies are used by each user so that the division is done for multiplexing of the signals. Now what is multiplexing? Multiplexing means when more than one user are going to use a common channel and which are divided in frequency domain, which are divided in frequency bands, then that is known as frequency division multiplexing, and that comes under this multi-carrier modulation system. So that each sub channel is associated with a carrier that is given by Fi, that is the frequency, intermediate frequency, which is given by F0 plus I minus 1 into delta F. Now I can vary from 1 to capital N, which is the mid frequency in the ith sub channel. So this is how the intermediate frequency or the sub channel frequency will occur. Now next is this, if the subcarrier are orthogonal over the symbol duration Ts, then it is referred to as orthogonal frequency division multiplexing. So nowadays this OFDM is very common, it is used very much and it is very popular, orthogonal frequency division multiplexing. So what is the difference between simple frequency division multiplexing and orthogonal? In case of orthogonal frequency division multiplexing OFDM, the subcarriers are all the subcarriers or all the carrier signals that we are using for multiple users, all are orthogonal in nature. And in case of FDM, the carrier signal that we are using for different users are not orthogonal, they are just shifted by some time duration. So that is the main difference between OFDM and FDM. So the OFDM concept utilizes the parsing of the input data bit stream into n symbol streams, each with a symbol rate that is given by 1 upon Ts. So that is nothing, it is the 1 upon Ts symbol rate, and each of which in turn is used to modulate the parallel synchronous subcarriers. So with an OFDM system having n number of subchannels, so these are the n number of subchannels, the symbol rate on each subcarrier is reduced by a factor of n relative to the symbol rate on a single carrier system. So this is the data, and we are receiving serial data. Serial data means it is in the form of 1 and 0, since it is a digital communication. So 1 0 1 1 1. So like this, the number of bits will act as an data. These are provided to this serial to parallel converter. So this will going to convert the digital data into this parallel form. Then the k number of bits will be segregated together, and then these are added, and we are getting this OFDM signal. Now this OFDM signal, the subcarriers are orthogonal in nature. So what is the basic principle of orthogonality? Two periodic signals are orthogonal when the integral of their product over one period is equal to 0, and they have integral number of cycles in the fundamental period that is given by for n is equals to period of k samples. Now you can see for the continuous time in the continuous time domain and in the discrete domain, like in the continuous time domain it will be extend from 0 to t, and you can see that this is the property of orthogonality when we are considering the continuous time signal. And when we are considering the discrete time signal, then the orthogonality principle is given by k is equals to 0 to n minus 1 cos 2 pi k n by capital N multiplied by 2 pi k m by capital N is equals to 0, and it is also there is a condition that n should not be equal to m. So that is the condition for orthogonality, to check whether the two signals are orthogonal to each other or not. Like these are the two signals, there are two successive pulses are there, which is st and st minus t. Even though st has long tails, the figure shows a tail passing through 0 amplitude. So this is 0 amplitude at the instant t is equals to t, when s is t minus t is to be sampled. So likewise, all the tails pass through 0 amplitude when any other pulse of the sequence is to be sampled. So they basically satisfy the orthogonality condition. Now you can see over here, like this is the frequency domain of these figures, like SF and ST minus T, the shifted version. So this is how this the Fourier transform or the of the rectangular window will be a sinc function, and this is how it will look like. So the sinc function is there for ST, and for ST minus T means for the shifted version. Now next is the subcarrier setting conceptual representation. So this is the diagram in frequency domain, and this is in time domain. Now you can see for the different frequency bands, this is the combined diagram. Like this is at frequency f1, then f2 frequency, f3 frequency, and f4. So these are the 4 different frequency ranges. Range will be there, that will be shown in this combined form. And in case of this time domain, now you can see that 4 different signals are there. Like this is for the first frequency. Now you can compare that f4 frequency is far greater than f1 frequency. So this is the frequency time domain representation. This is first frequency, this is second frequency, third one, and fourth one. So fourth frequency is quite larger as compared to the frequency 1. And this is the combined signal for all those 4 frequencies. So this is how you can see that how this subcarrier setting will be there. So what is required in multi-carrier modulation, that different carrier signals is required at different means it should not be same, it should be orthogonal in case of OFDM, and when we are considering the simple FDM, so orthogonality is not required. So this is the representation of the different frequencies that we are going to consider for OFDM modulation. Now example of 4 subcarriers with 3 symbols per subcarrier at OFDM modulator stage. Now you can see over here that this is the diagram which is showing the frequency versus time graph, and these are the symbols. So this is basically used for the OFDM modulator. This is for S1, S2, S3, S4. So this is how you have to divide the frequency range. Like 4 different frequencies are there, and how this constellation diagram of OFDM is drawn. So this is the constellation diagram of this particular signal. Now you can see at frequency F1 there are 3 different points are there. So at frequency F1 we are showing these 3 points. At frequency F2 we are showing these 3 points like S4, S5, S6, then at frequency F3 and at frequency F4. So this is the 4 subcarrier concept. Like 3 symbols are shown, each at a single frequency, and these frequencies are separated by a distance that is denoted by delta F. Now next one is the concept of carrier frequency allocation to symbols, a typical case in which 3 symbols are assigned to a carrier. So serial to parallel conversion and mapping into frequency domain components after modulation. So you can see in this diagram that this is the OFDM frame. So this is how the symbols are assigned, their time slots. That frequency F1 is given as these 3 symbols, S1, S2, S3. This is for F2 and so on. This is for F3, and then F4 will be there. So this is the OFDM frame. Now OFDM block assigned to a carrier, that is serial to parallel conversion is there. So S1, S2, S3, etc. are representing bits per symbol or words according to the modulation method selected, that is bits per word or 3 bits. That is symbol for 8 PSK. So this is for frequency F1. Now you have to multiply this 3 symbols with frequency F1, another 3 symbols with frequency F2, then 3 symbols with F3, and then for F4. So this is how you have to multiply the symbols with the corresponding frequency. So this is for the OFDM symbol, or that is the time duration is denoted by TS. Now you can see After multiplication, how this sinc function looks like, this is for frequency f1, this is centered at f2, f3 and f4. So the sinc function diagram is shown over here. Now, if the modulation scheme used on the ith subcarrier can accommodate ki bits per symbol and the subcarriers are spaced by 1 upon ts hertz, where ts is nothing, it is the symbol duration of the subcarrier, that is delta f is equals to 1 upon ts, then this condition is for the orthogonality and the relation between the symbol duration of the subcarrier and the then for the OFDM is given by this particular formula, that is the relation is Ts is equals to n into T OFDM. So by selecting n to be sufficiently large, the symbol interval Ts of the subcarriers can be made significantly large than the time duration of the channel time dispersion. So hence the ISI can be made arbitrarily small by selecting the value of capital N. So we can change the value of n to maintain this particular relation, that is Ts is equals to n into T OFDM. Now next we move towards DFT and IDFT implementation of OFDM. So DFT is discrete Fourier transform and IDFT is inverse discrete Fourier transform. So this Fourier transform is used to implement the OFDM because we want to generate carrier signals which are orthogonal to each other. So n number of, let's say, users are there, so n number of carrier signals are required at the transmitter side and at the receiver side which are orthogonal to each other. And that will be implemented using this DFT and IFD procedure. So let xk be a symbol sequence which is used to modulate n simultaneously transmitted subcarriers. So fk will be equals to f naught plus k minus 1 by ts hertz. Let t naught is equals to ts plus delta. Then k will vary from 1 to n minus 1. So where ts is the symbol duration of the subcarriers and delta is the guard time interval that is assumed to occur at the start of a new signaling period. So which is used to minimize the, basically used to minimize the ISI effect, that is the intersymbol interference effect. So OFDM is generally used to minimize the ISI effect because we are using the carrier signals which are orthogonal to each other. Then the OFDM signal in the complex baseband signaling can be written as xt is equals to 1 upon under root n summation I is equals to 0 to n minus 1 xi e to the power j 2 pi it by t8. Now small t will vary from 0 to t8 plus delta. So this is how the variation of this xt signal will be there. In case of, this is nothing, this is the DFT formula, how you have to calculate the DFT formula, DFT of a particular given signal, continuous time signal. Now the time interval sampled at t is equals to kt OFDM yields a formula, that is xk t OFDM is equals to 1 upon under root n. Now I will vary from 0 to n minus 1, that is xi e to the power j 2 pi I k t naught f t OFDM divided by ts. So which is the inverse Fourier transform. Thus we can generate xt by IDFT. So DFT and IDFT both are shown for this particular OFDM signal. Now this diagram is showing shows the OFDM implementation by IDFT and DFT. Now you can see over here, like this is the serial data, which is nothing, it is the bits of information, n number of bits we are taking, which is applied to the serial to parallel converter at the transmitter side. Then these parallel information is we are going to apply this IDFT algorithm to convert to take the inverse Fourier transform DFT of the input signal. Then D2A converter is used at the channel. We are using this A to D converter. So this is digital to analog and this is analog to digital converter. And then after analog to digital converter, DFT is used. DFT is discrete Fourier transform that will going to perform the Fourier transform of the digital data. Then the parallel to serial converter is there, that is just the reverse part of this particular blocks which are used at the transmitter side. Then the estimated data will be there. Why we are using this estimated data? Because at the channel there will be AWGN noise or other effects which will going to change the characteristics of the signal. So after demodulation or after parallel to serial converter, it may be possible that the actual data, let's say I have transmitted 1011, then only single bit is not recovered, or 2-bit error will be there or 3-bit error will be there. So that comes under the estimated data, because we are not sure that whatever we have transmitted, we have received it correctly. So that is the estimation, that is about the estimated data. Now next is limitation of multi-carrier modulation. So a major problem with the multi-carrier modulation in general and OFDM system in particular is high peak to average power ratio, that is PAR. PAR is a parameter that is used to visualize the efficiency of this MCM system that is inherent in the transmitted signal. So large signal peaks occur in the transmitted signal when the signals in the N subchannels add constructively in phase. So such large signal peaks may saturate the power amplifier at the transmitter and thus cause the intermodulation distortion in the transmitted signal. So this is the limitation of MCM. Now next is zero intersymbol interference communication technique. So till now we have discussed that what is multi-carrier modulation technique, and if these carrier signals are not orthogonal to each other, then there may be possible that ISI will going to affect the quality of the signal. So to minimize the ISI, we have to see that what we can do so that ISI will be reduced. So ISI is a form of distortion in a signal. Here a received symbol interferes with the subsequent symbols, which makes the communication less reliable. So ISI is caused due to the multipath propagation or the inherent nonlinear frequency response of the channel. So ISI between the pulses or symbols is ideally shown by this, like this is the ideal waveform. This one is also ideal waveform, but this is affected with ISI, and this is basically how the overlapping of the pulses will be there, because when it will going to travel over the channel, it will going to spread. So this is the spreading of the pulse. Actually it should be like this one, there should be sharp transition at this point, but due to the effect of noise and the spreading of the signal, this will going to interfere with the next waveform, and this is known as the effect of ISI. So Nyquist criteria for zero symbol interference will be there. Nyquist showed that the theoretical minimum bandwidth needed to detect the RS symbols without ISI is given by RS by 2 Hz. So this is the minimum bandwidth that you have to consider. Instead of using RS, we have to consider RS by 2 so that ISI will be reduced. So the sync shaped T by S pulse is called the ideal Nyquist pulses. Its multiple lobes comprise a main lobe and a side lobe that are infinitely very long. So infinite number of side lobes are there and only one main lobe is there. So this is the concept of Nyquist criteria for which we have to consider minimum bandwidth, that is RS by 2, so that ISI will not be there. So this is the bandwidth constraint and Nyquist filter. If we operate the system at smaller bandwidth, then according to the Nyquist condition, the pulse would spread in time, which would degrade the system bit error performance due to the increased ISI. So there is a bandwidth constraint, because in case of Nyquist criteria, we have reduced the bandwidth to RS by 2, which is just half the original bandwidth. So due to this, there will be bit error, rate will be increased, and this will going to increase the ISI. So there should be a balance, should be maintained between bandwidth and the spreading of the pulse, so that the ISI will be reduced. Now next is filtering, that is pulse shaping. How we have to shape the pulse so that the equalization will be there and the signal quality will be maintained. So this is the diagram like this is nk, number of bits will be there, this is n1, n2, this is just the representation of the amplitude. Then this is passed through a filter, that is a transmitter filter denoted by HTF transfer function. This is HCF for the channel transfer function, this is HRF for the receiver channel transfer function. So this is how the pulse will be transmitted. This is the spreading of the pulse. Now you can see that the spreading of the pulse will be there. Now we have to select, we have to sample this particular signal at t is equals to kt, and then it is detected. So you can see that this is nk and this is n dash k, that is again the estimated version of the input signal. So this is pulse shaping. Now, there are different filters that we can use for pulse shaping, like first one is the raised cosine filter. Now, raised cosine filter, for this particular thing, the total bandwidth W will be symbol rate multiplied by 1 plus alpha. Alpha is the roll-off factor that plays a very important role in raised cosine filter. Depending on the value of alpha, the curve of this particular filter will going to vary. This is written over here, this is roll-off factor for the raised cosine filter. Next one is the square root raised cosine filter, that is we are using the root raised cosine filter which is passed through an ADC, that is analog to digital converter. Then it is passed through a modulator and through an antenna it will be radiated. Then again we have to use the same root raised cosine filter at the receiver side, demodulator and detected bit. So this is very simple, you have to use this particular formula to visualize this square root raised cosine filter. Next is the Gaussian pulse shaping filter. Its PDF is same as we have learnt earlier, that is the Gaussian distribution. And why we are using this Gaussian? Because the transformation and inverse transformation of this Gaussian pulse shaping filter is same, its shape is same. So that is the Gaussian distribution pulse shaping filter. Next one is the Chebyshev ripple finite impulse response. Now Chebyshev is somewhat like the Butterworth filter. There are two types of Chebyshev filters are there, type 1 filter and type 2 filter. Type 1 filter is a all pole, has an all pole transfer function, whereas this type 2 is a low pass filter with both which has both poles and zero. So that is the difference between Chebyshev filter. Now you can see that this is the pass band and this is stop band. Stop band has larger number of ripples as compared to the pass band. Next is the windowing technique. So there are 4 to 5 different windows are there, like Hamming window, Hanning window, Blackman window, Bartlett window. So there are 4 to 5 different windows are there through which if the signal is passed, then it pulse shaping will be there and ISI will be reduced due to this windowing technique. Then this is the detection strategies. If we are using an hypothesis criteria, like this is the hypothesis, there are two types of hypothesis are there, H0 and H1. Depending on that, we can also detect or we can also reduce the ISI, that is based on this detection strategies. Now next one is the matched filter. There is also a matched filter which is there are two types of filters are there which are used at the receiver side, like first one is the matched filter, another is the optimum receiver filter. In case of matched filter, it correlates the incoming signal with a locally stored reference copy of the transmit waveform. The matched filter maximizes the signal to noise ratio for a known signal. So this is how the transmitted signal will looks like. Then it will be passed through a channel which over which there will be a noise that will going to affect the quality of the signal. Then it is passed through this integrator and then we have to select the largest among the two values that is affected by this particular carrier signal. So this is all about today's lecture, where we have discussed the ISI and how we can reduce the ISI due to with the use of different techniques and pulse shaping filters. Thank you.